Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025, about 2 days ago. It introduces a debiasing method that yields a 15% performance gain, which is equivalent to using 2.5 times more pre-training data. The paper is titled, "Is Diversity All You Need for Scalable Robotic Manipulation?" and its findings challenge some common assumptions about training robot models. The authors investigate data diversity for robot learning, finding that while more tasks are good, using data from more robot types isn't always necessary. Also, the authors shared their full AggieBot World platform on GitHub, and it's really comprehensive. Listeners will find the massive dataset with over 1 million trajectories, along with scripts to visualize the data and a Jupyter notebook to quickly get started with policy training. It's a complete toolkit for researchers. Alright, this first figure really breaks down the core findings into 3 key areas of data diversity. First, task diversity, which means teaching the robot many different things to do, is shown to be very beneficial. The chart shows a predictable scaling law. As pre-training data increases, the optimality gap, which is just the difference between the model's performance and a perfect score, steadily decreases. Next, embodiment diversity, or using data from different robot bodies, is shown to be optional. A model trained on one robot can still transfer its skills to others. Finally, expert diversity, meaning different human demonstrations, can actually confuse the model. The author's debiasing method improves performance by 15%. Building on that idea of expert diversity, this next figure illustrates what the authors call multimodality, which just means there are multiple correct ways to perform a task. On the left, we see spatial multimodality, where a robot can push an object from different directions. This is actually helpful for learning. But on the right, the figure shows velocity multimodality. Here the robot follows a similar path but at different speeds. It turns out this velocity variation is what really confuses the model, and identifying this specific problem is key to their debiasing solution. And this brings us to a really key result, shown in these 2 plots. On the left, we see the GO1 model's average score improves steadily as it's pre-trained on more demonstrations, from none up to 1 million. The chart on the right then shows this improvement follows a predictable power law relationship. A power law relationship is just a specific mathematical pattern where performance scales in a very regular way as you add more data. The correlation coefficient, R equals negative 0.99, confirms this is an almost perfect, predictable trend. This table then puts these ideas to a real-world test, focusing on that question of embodiment diversity. It compares 2 models, RDTOXE, which was trained on the OpenX embodiment dataset containing data from many different robots, and RDTAWB, trained only on the single robot AggieBot World dataset. So when both are tested on a new robot arm, the RDTAWB model, the one trained on just a single robot type, actually achieves a higher average score. This result really reinforces their surprising conclusion that multi-robot training data might be optional for effective transfer learning. Okay, so now let's look at the impact of that debiasing method we talked about earlier. This table really quantifies the improvement. It shows what happens when you apply distribution debiasing, which is their technique for correcting confusing variations in the demonstration data, during both pre-training and fine-tuning. We see that when both the initial and the specialized training data are debiased, the average score jumps from 0.46 to 0.53. That's a 15% gain, which the authors say is equivalent to training on 2.5 times more data. So, that 15% boost really highlights the overall message here. When it comes to training robots, not all data diversity is created equal. The key takeaway is that while having a wide variety of tasks is crucial for learning, having data from many different robot bodies might actually be optional. More importantly, certain kinds of diversity, like different speeds in human demonstrations, can hurt performance. Correcting for that confusion leads to much more efficient learning. That's all for this week's AI Research Roundup. Thanks for tuning in.